Yeah, hello and welcome. I would like to thank you for your interest in our work. Uh, my name is Ramoni Adeogun. I am an assistant professor with Wireless Communication Network section at the Department of Electronic Systems here at Aalborg University in Denmark. So in this talk, I would be uh, presenting our work entitled Learning to Dynamically Allocate Radio Resources in Mobile 6G Subnetworks. So basically what we have done here is to develop machine learning approach for the dynamic selection of frequency or time frequency or resources in a recent year sixth generation INES subnetwork, where the term INES actually stand for inside everything. We would see why in the next few slides. So here's an outline of what we would be going through. I would actually introduce the general concept of SSG in itself. Would then, discuss the algorithms we have actually investigated for implicit management of interference in a network comprising of a number of such cells. We will see some results, and finally we would try to summarize the talk and then conclude. So 6G INES subnetworks, as we actually call them, these are short-range, low-power cells with extreme communication requirements. So they need to actually satisfy a very low, a high reliability, or perhaps multi-gigabyte data rate within a very short latency. So we actually envisage a latency of around 100 microseconds, for example, right? So why do we call them INET? So these short range cells, they actually envisioned to be deployed in specific entities such as robots, production modules inside vehicles or aircraft, or even on human body. So why short range, right? So, and why do we actually conceive them to operate with low power? As we would expect, having a low power cell or cells would actually enable aggressive reuse of the spectrum, and we would then be able to actually offload the most demanding services in terms of the latency requirement and of course the reliability requirement from the traditional micro or macro networks, right? Having a short range cell on top of that actually allows us to have low delay spread, which means that if we are discussing about OFDM type of waveform, we have short cyclic preface requirements, and hence we have a limited overhead. Now, these cells are mobile. We have this extreme requirement that they need to always satisfied regardless of the environment or the channel or the interference conditions. The problem is a bit more complicated here because we have basically assumed that there is no central controller that would actually manage how resources are used by each of the cells. So this means that the interference management has to be done in a completely distributed manner, with each cell relying on its own local information to be able to uh, decide on where to actually transmit. So a few examples of use cases for the HINET cells. This is from some of our earlier articles. So if you are interested in actually reading more, you can then just look them up here. So what we have here is an infantry example where we are actually expecting that such in a cell could, for example, be deployed to remove the last cabling in the control of the arms of the mobile robot. Inside vehicles, we could also have controlling the CAN bus, either ignition control or even brake control and all that, or in a human body where you want to wirelessly control, for example, a heart pacemaker, right? So as you can all see, this represent very life critical use cases. So which means that on top of the extreme requirement, we need to have some level of spatial temporal guarantee or extremely high availability. So here is just a brief summary of an early design of here interface or numerology and all that for such in itself. So as you would expect, because of the extreme low latency, if we are looking at an OFDM transmission, then you would expect that we have large subcarrier spacing such that we can have super short here symbols and all that, right? We have actually introduced a couple of technology components to be able to meet the high reliability requirement. For example, expect that we would have blind repetition, of course, with robust coding and all that, right? And then we would like to actually combine that with upping of the same transmission over multiple channels such that we can actually harvest interference diversity as well as combining gain. So for the study here, we will rely on this type of a symmetric frame structure where basically we have a symmetric uplink and downlink, and then depending on the number of repetitions allowed, we can fit a maximum number of devices in each subframe. So I would like to just mention here that a device here is actually used to describe an ensemble of uplink and downlink transmission. So uplink could be from the sensors to the controller, which serves as the access point in each of the cells, and the downlink from the controller to the actuators. So now to distributed management of interference. So basically here it's we have a number of mobile cells, each cell having an access point and a number of actuator sensor pairs and all that. And they need to actually operate over a shared spectrum kind of. We actually assume that we have a total bandwidth of B, right? And this is divided into a number of equal channels. So in this case, we have 12. Now the question is, each cell needs to have blind repetition a number of times. Do we allow them to actually operate over the entire band such that you could choose anywhere to transmit? The problem we actually foresee here is that jumping from band which are actually widely separated may be a bit problematic, and as such we decided to restrict transmission within each cell at a given time to a group of channels, right? So in an earlier studies, which is actually reported here, we have looked at a number of heuristic algorithms for enabling this dynamic selection of groups and then evaluating the performance. And our conclusion is, as we would expect, we can actually get large improvement in spectral efficiency or reduction in the resource requirement to support those extreme requirements, but at the expense of relatively complex algorithm. For example, we have this nearest neighbor conflict avoidance, which basically assumes that each cell is able to determine exactly where the closest or the nearest neighbors are actually operating, and as such, it can basically just avoid selecting such a channel, right? But what do we actually do in this article? In this article, what we have done is to look at how we can actually use machine learning framework to perform implicit or distributed selection of resources in order to satisfy this requirement for the inner subnetworks or cells, right? So we foresee the ability to be able to train a neural network to map local sensing information at each cell to resource selection. But the problem here is, how do we generate data to be able to train the neural network such that can then perform this mapping? So we basically actually assume that we have a simulator which gives a relatively okay, data generation compared to what we would say real deployment. And as such, we can then simulate or synthetically generate data to train those networks. So the step in the proposed algorithm actually in, in, involves centralized generation of data. So which means that we run this simulator, which is centralized algorithm, which in this case is a centralized improper graph coloring algorithm, where we basically assign a maximum of k colors, where k is the number of groups to all the cells based on the interference coupling or mutual coupling matrix between the access points in the cell. We then convert this information into a form that represents the local aggregate interference power at each cell on each of the channel group, where the entry years are actually averaged over all the channels within each group. The task now is to train the neural network to learn this mapping from this aggregate interference power to the actions, or in the case of graph coloring, colors. And then once the network is trained, we then deploy the same neural network at each controller or access point to perform selection, and then we then evaluate the performance. To start with, we needed to generate data. What we have done is to synthesize or simulate such environment with 16 mobile inner cells having 18 devices, and then each one having a radius of these, and then we generated the data and then trained the neural network with 2 layers as a start, just to see what would happen. And here's what we actually observe from the training, right? What you have here is the accuracy, which basically measures how we exactly able to select the colors assigned by graph coloring based on this aggregate measurement. And it seems like we can do that with an accuracy of around 80%, which one would say is not really good. And how well this actually translates to in terms of the communication theoretic requirement, it's a question that needs to be addressed. So for that reason, we basically evaluated another metric during the training, which we actually call the mean absolute power difference, an average of the difference between the interference power on the group selected by the DNN and the one that was actually assigned by graph coloring, which was used for data generation. And interestingly, we actually observed that we only have a fraction of dB difference between the 2 powers. So which actually intuitively means that even in those 20% instances where the neural network fails to reproduce exactly the colors of the coloring, it still selects a fairly good pattern, and as such, we would expect to have reasonable performance. So now let's go into evaluating the performance of the algorithms and compare the DNN we thought about. To do that, we need to actually define a couple of metrics that we will be using in evaluating the algorithm. So here we will be discussing probability of loop failure, where, as I said, a loop here is an ensemble of uplink transmission from sensor to controller and the corresponding controller to actuator downlink transmission, right? So we would say that a loop has failed if the achieved SINR on either the or both the uplink and downlink is below that is required to achieve an outage of at least 1E minus 6, right? And then we define an average, which is like a probability that a loop will fail to meet those requirements as an average of what we call Rn here. So we are Rn is the ratio of the number of failed loops at every to the total number of loops at every transmission. Instant. We would also actually evaluate the time between occurrence of what we call failures here as the average time between switching to measure the overhead incurred by each of the algorithm. Here is an example result where we have evaluated the PLF against the bandwidth per channel. And here we had 12 channels, 6 groups. So which means that each channel has a maximum of 2. Each group has a maximum of two channels, and correspondingly 2 transmissions are allowed. Look at the plot here, you see that the DNN performs similar to other heuristic algorithms, and in fact, the DNN and the 3D are slightly better than graph coloring at IPLF. So one thing could be, this could be due to the fact that the graph coloring itself is not necessarily an optimal algorithm, or it does not guarantee optimality of the solution. On top of that, we have done some kind of improper coloring, so which may actually explain why we have these issues here. Another thing that we have looked at is to now look at the distribution of the ratio of failed loop, just to understand the relative performance of the distributed algorithm. What we can see from here is that it appears that the NNCA is better on an instantaneous basis compared to greedy and DNN, but that is not noticeable in the average curve. So now we have done some sensitivity analysis, which basically we are trying to evaluate the relative performance of the DNN algorithm with environment parameters different from those that was actually used in the training. If we change for example, the power loss exponent or the shadowing standard deviation, does the DNN-based approach fail completely? And the answer is actually no. It seems like the relative performance of the algorithm remains fairly same regardless of the environment condition, which is an advantage. So on the side here, we have the average time between switching of channel. Ideally, we would like to make this as large as we can, such that means that we are actually jumping from one link to another at a very slow rate, right? And what we see here is that DNN appears to have the best or the highest time between switching, followed by the greedy. So which means that these are actually better algorithms in terms of the overhead incurred, right? Just to actually summarize the talk, I have shown you recent 6th generation subnetworks, which are short-range low power cells that are meant to support extreme requirements in terms of latency, reliability, or even data rates. So the cells can be deployed inside robots, vehicles, body, or even aircraft. So we have shown how a neural network can be trained using data generated from coloring to perform distributed implicit selection of resources based solely on local sensing information, and we saw that we achieved even slightly better performance than the centralized baseline, except at the tail of the PLF, where we saw a flattening of distributed scheme. Our ongoing research effort is actually investigating what can be done to bridge this gap between the centralized approach and the distributed approach, if at all we can. And a couple of options, for example, relying on recurrent neural networks such as LSTM and all that, to learn trends of patterns in the sensing measurement and then translate that into better selection decisions. An alternative could be to start exploring other non-radio information and how those can be used to, design implicit interference management algorithm and all that. One last option could be to enable signaling among the cells. This is actually only possible for selected use cases, for example, industrial environment. But if we go to the in-vehicle, in-body and all that, it's not likely that we will be able to have a central controller, or that we will be able to enable communication among heterogeneous networks or entities, kind of. That's basically it from me. If questions, please feel free. Let's try to use the chat provided by the conference. And if you have any questions or what have you, please write us an email and we endeavor to actually respond. And yeah, thank you for listening.